Okay, so today we're very happy to have Professor John Cardy from Berkeley and Oxford to tell us about physical interpretation of the TTbar deformation in 2D field theory. Please, Professor Cardy, take it away.
Yes, okay. It's a great pleasure to be giving a talk at the Kadanoff Center. Leo Kadanoff was a great friend of mine and a mentor for me very early on in my career when I was contemplating switching from high energy physics to statistical mechanics. Although a few people might say that I never actually entirely made the switch, but because here I am talking about two-dimensional field theory. Yes, anyway, I'm going to talk about some work that I've been thinking about in the last year or two. And most of the work from the physics point of view, I still haven't completed writing up, so that's in preparation. But I did realize that it had some interesting applications to mathematics, and I wrote that up in a short paper, which I put on the web last month. So I will be mentioning that also as I go along. And I hope you interrupt me if you have any questions. So I assume that most of you have heard a little bit about the TTbar deformation. I'm just trying to advance my slide here. There we go. But I will give you a very brief introduction, and then I'll talk about the physical interpretation, which will be in the language of Magneto-elasticity. That is the coupling of the underlying quantum field theory to an elastic medium. And then I will talk about how we relate the fixed strain ensemble to the fixed stress ensemble. It turns out that from this point of view, most of the previous work has been done in the fixed strain ensemble, where the equations are relatively complicated. And if you look at them in the fixed stress ensemble, they're much simpler. So I will explain that. And then I will go on to the mathematical interlude, where we realize that a lot of the equations that we've talked about actually apply in a much more general mathematical context of TTbar deformed modular forms and so on. And then I'll go back to the physics and I'll explain how everything becomes simple if we relate the fixed strain ensemble and the fixed stress ensemble by a Legendre transform. And then the equations have this interpretation in terms of a two-dimensional fluid, and the formation of shocks or the collapse of the fluid corresponds to the familiar singularities of the partition function that we find at fixed strain. Okay, so I will continue. So here is a very brief introduction of the way I think about how a quantum field theory emerges out of the scaling limit of a lattice model. And so this is coming at it from a statistical mechanics point of view, and I'll be working entirely in flat space. So, as you know, if you take a critical short-range lattice model like the icing model, then you can take the scaling limit as the lattice spacing goes to 0, and it gives you a local Euclidean field theory. And then observables like the magnetization, energy density, etc., all correspond to local fields, and on scales much less than the correlation length, or exactly at the critical point, they have a power law decay with some characteristic exponents here which are related to the conformal dimensions of the operators involved. And a particularly important one, as you know, is the stress energy tensor, which in quantum field theory is called the energy momentum tensor. And it's interesting that in the context of the two-dimensional Ising model, this object was first identified by Kadanoff and Saber in 1971. All this was around the time that the connection between statistical mechanics models and the operator product expansion and that kind of thing was all being understood at the time by Leo and his friends. Anyway, you can think of this as the response of the free energy to an infinitesimal change in the metric in the usual way. But of course, it also corresponds to the note occurrence of translational symmetry. And in d-dimensional Euclidean space, the stress tensor has dimension d. Now, from this, you can form 2D, you can form dimension 2D scalar bilinears by contracting indices. Of course, the trace is 0 at the critical point, but it turns out that once we turn on the TTbar deformation, that's no longer going to be 0 because the theory is no longer invariant. Now, these T-squared terms are the dominant irrelevant terms in many two-dimensional lattice models. So they are, because they have dimension 4 in 2 dimensions, they're irrelevant in the infrared, but that means that they're relevant in the ultraviolet. So you would expect them to correspond to terms which are ultraviolet infinite, but that is corrections which depend explicitly on the cutoff. But what Homologico showed in 2004 is that if you make this particular combination here, which is essentially the determinant of the stress tensor, which can also be written like this, then many features of the deformed theory are in fact finite and are solvable in terms of the original theory. So quantities like the partition function on the torus, for example, are ultraviolet finite, and even correlation functions of local operators have only logarithmic divergences, it turns out. So this is interesting because it's an example of a non-local with some kind of ultraviolet length scale. So it's an example of a finite ultraviolet completion, which is not a local quantum field theory. If you try to understand its effect in a massive theory, it effectively gives a particle of mass m a kind of a width in space of size lambda m in the rest frame of the particle. And that is equivalent, when you think about the scattering process, is equivalent to either a positive or a negative time delay. And what this does is to give a rise to rather simple CDD factors multiplying the S matrix. It's also interesting in terms of the ADS CFT correspondence, because it's been proposed that if we take negative lambda, it corresponds to going, quote, into the bulk. But I won't be talking about that anymore. So there are several peculiarities, of course, of this TTbar deformation. As logic I've showed, if you think about it in 1+1 dimensions, if space is a finite interval or a circle, then the eigenvalues of the Hamiltonian evolve according to an equation which is simple but non-linear. And the fact that it's non-linear gives rise to a singular behavior of the solution. If the undeformed theory is a conformal field theory, then the undeformed eigenvalues all scale like a constant over R, and then this solution of the equation looks like this, with this all-important square root here. And you can, which obviously gives rise to a singularity if lambda c is negative. You can also express this in terms of an equation here, and so basically E0 goes like E lambda squared for large E. And because the density of states in the undeformed conformal field theory goes exponentially with the square root of E, that means that if lambda is positive here, then the density of states in the deformed theory is increasing exponentially with E lambda, and that means that the Laplace transform of this does not exist for sufficiently high temperatures, and therefore the theory is said to have a maximum temperature, which is sometimes called a Hagedorn transition. If lambda is negative, on the other hand, then there's a maximum in the density of states, and then we find that, at least from a thermodynamic point of view, then if we only include the real eigenvalues with a positive entropy, then we get a finite entropy density at infinite temperature, rather like what happens in a lattice spin system. So one aim of this work, which of course all these things have been remarked on in the past, one aim of this work is to try to explain the phase features in a slightly different physical setting, where, for example, we can understand whether the partition function is modular invariant or not. Because, for example, in the k square lambda is negative because only a finite number of states are going to contribute to the partition function. It's hard to understand how the partition function on the torus could be modular invariant, but we will see that there is a sense in which it is. Okay, so I'm now going to talk about this other interpretation, and that is in terms of Magneto-elasticity. So I'll give you a very brief undergraduate level description of this. It's the coupling of the magnetic degrees of freedom to the displacement field of an elastic solid. And for example, this is responsible for the phenomenon of magnetostriction, that if you put a bar magnet in a magnetic field, it changes shape. And of course, we here are not necessarily going to be considering magnetic degrees of freedom, though it might be if we were talking about an Ising model. But in general, we can think about coupling other, what I call matter internal degrees of freedom to the elastic degrees of freedom. And the coupling is going to be in the standard way of the stress times the strain. So it's going to be the integral of the total stress tensor times the strain tensor. And of course, the strain tensor, when expressed in terms of the displacement field, has a form like this. And the total stress tensor is going to be a sum of the elastic stress tensor and the matter. And also, as soon as we turn on the coupling at a finite coupling, there is going to be some contribution from the coupling also. But I'll just lump these together in what I'll call T matter. So the other relation we need is how to express the elastic stress tensor in terms of the strain field. And of course, this is a generalized Hooke's law. And for an isotropic medium, it has the form written here where mu and lambda bar are the Lamé constants. So how does this work? Well, if we think about the partition function of the whole system, it's an integral over the matter degrees of freedom and the strain degrees of freedom. And so here's the coupling of matter to the strain and the coupling of the elastic stress tensor to the strain, which of course is quadratic. So because it's quadratic, we can integrate out the strain field and get something which is quadratic in the matter stress tensor. And of course, then because this is a Gaussian integral, it's dominated by its value at the saddle point, where epsilon is the inverse of this matrix lambda times the matter. So in order to get the TTbar form, I will call then we need to take lambda to be small lambda times epsilon, and therefore our relation between the strain field and the stress field is going to be as written here, or writing it out in components, it looks like this. So that means that that means that this is a very strange material, because a stress in the two direction is going to produce a strain in the one direction and vice versa. And the sign of the transverse response is opposite to that of the longitudinal response. So this material actually has what we call an infinite Poisson's ratio. So if we have a normal material and we have a block of this here with a positive finite Poisson's ratio, if we put a weight on this, so we compress it in the vertical direction, then it squeezes down in the vertical direction, but it extends in the horizontal direction. If we take this strange material called, which I term TTbarite, which I hasten to add, we probably can't fabricate it in the lab. It would be interesting if we could, but we can't as far as I understand it. Then if you compress it in the vertical direction, or if you apply a weight in the vertical direction, it does not compress in the vertical direction, but just extends in the horizontal direction. But mainly what we're going to be interested in here is not this kind of experimental but rather a protocol where initially where we take a certain geometry like a rectangle or a torus and start the system in equilibrium with zero elastic coupling, where the only stresses are the Casimir type forces, because the system is at a critical point. And then we turn on this coupling lambda. Okay, so why is TTbar solvable? Well, there are many different ways to say this, including a coupling to random geometry, the fact that we can write the determinant of T as a derivative of a local field, of a non-local field, excuse me. But the easiest way is this idea that it's equivalent to a coordinate transformation, or in our case, a displacement which is proportional to the stress tensor itself. So we had an equation here that if we make an infinitesimal change in lambda, then the change in the stress is proportional to the stress tensor. And remembering that epsilon was essentially the symmetrized derivative of the displacement field, we can write an equation that looks like this. And the only important thing to note, which is essential to the TTbar deformation, is that the TTbar deformation is a flow. It's not just a simple perturbation. That we're not just taking the stress energy tensor of the undeformed theory and adding a certain amount of it to the action with a finite coupling. So if we integrate this equation with respect to x, what we find is that the evolution of the displacement field can be written as an integral over some contour from some fixed point capital X up to X of the flux of the conserved current T across this curve here. And because T is conserved, very important, this is in fact independent of the actual contour. If we had something else another combination of T and T bar, which wasn't exactly the determinant of T, then this would not happen. So it's essentially this fact that makes it solvable. So here we are. If we have a point x1 and a point x2, if we then the change in the displacement of at the point x1 minus the displacement at the point x2, I'll call R12, is proportional to the total flux across any curve which might happen to go through X and does not have to. Any curve, any simple curve connecting X1 and X2. So the point of view, so I want to stress that this is almost identical to the point of view which has been expressed before in the literature. But here I'm trying to think about U as being a matter field. And so I'm not treating this as a diffeomorphism. Otherwise we get into the slightly paradoxical situation of saying that a change in the coordinate is proportional to an operator, which of course is what happens in a sense in a theory of quantum gravity. But I'm trying to make this as simple as possible. I want to stress that the frame of reference before we turn on the coupling to elasticity gives us an absolute frame of reference, and there's no requirement of general variance here. So it gives us a very easy way of understanding what the TTbar deformation is, that the change in the separation between 2 points is basically an epsilon symbol times the force acting across any curve between the 2 points. Now, the nice thing about this point of view is that we can actually take these points to be macroscopically separated, and then we can choose a thermodynamic ensemble in which the force acting across this curve is non-fluctuating and indeed independent of lambda. And in that case, R lambda evolves linearly with lambda, and we get very simple equations for the evolution of R in the fixed N ensemble. So an example here is the torus, which we can think of identifying the opposite sides of a parallelogram whose sides are the vectors in R2 or equivalently the complex plane R1 and R2. So we take R2 and we mod it out by a lattice generated by R1 and R2. And there are different ensembles here we can think about. We can either think about what in this language we would call fixed strain, which corresponds to fixed geometry. If we quantize the theory, if we think about the theory in 1+1 dimensions, so we think about R1 as space and time as being orthogonal to it, then this is basically the canonical ensemble, where we think about R1 as the volume and this direction as the inverse temperature. Or we could think about fixed stress, which corresponds from this point of view to fixed energy N2 and pressure N1. Or we can have some mixed ensemble, which is which is fixed R1 and N2, which is a microcanonical ensemble. So all these different ensembles are related either in statistical mechanics by the Laplace transform, or more traditionally by a Legendre transform. And initially, I'm just going to talk about the Laplace transform. So a Laplace transform looks like this, and I'm going to go through this very, very quickly. So we can always write a spectral decomposition of the partition function in terms of what's essentially the energy and the momentum. But because we're going to want to analytically continue this, it's useful to think of rho zero, which is essentially the density of state, as being the imaginary part of some complex function, omega zero, and so this is basically a contour integral in S2, where omega zero is the Laplace transform of Z of R. Or we could write it in terms of some double Laplace transform, where we go from the R1, R2 ensemble to what's essentially the N1, N2 ensemble when we pull back the contour in S1 and S2. So this is the framework in which we think about the TTbar evolution, which is given by, in the fixed N, fixed S in terms of that contour integral. It's given by an equation that looks like this. There's a mark on, so the thing that evolves simply under the TTbar deformation is not the partition function itself, but the partition function with a marked point, which is the partition function divided by the area. So this was a thing which took the fielders a long time to understand why, but this is basically the explanation of why. So that means basically that from this point of view, we should write the partition function per unit area as in a scaling form like this, where although the partition function is going to be modular, invariant z, small z0 is going to transform more like a modular form of weight 2. Anyway, in this, it's useful to understand the TTbar deformation in the mixed ensemble, whereby R1 goes into R1 minus lambda times the force or the stress in the orthogonal direction. Here I'm using a complex notation, which is the reason for the I here. And so basically the deformed partition function has the form here, the form that it would in the undeformed theory, except we shift the size of space by a complex amount, which is proportional to F. So that's why we need a definition of this with a complex R1, which is what the idea was on the previous slide. And then after a few pages of algebra, what we then show is that we can write the deformed partition function in the following scaling form, where the deformed small z, which I remind you transforms like a modular form of weight 2, is given by an integral that looks like this, where alpha is a dimensionless deformation parameter, which is essentially the original one, which had dimensions of length squared divided by the area. So this formula was originally derived by et al. From some considerations of JT gravity, and I derived it a little bit later. Also, so the main characteristic here is that the deformed quantity here, which happens to be a modular form of weight 2, is given by a kernel here, which is essentially something like a Selberg kernel in the upper half plane, integrated over the upper half plane with the invariant measure here, with some interesting factors here, which actually then ensure that the deformed partition function is in fact modular invariant. So if you take this form here, which is essentially equivalent to what I wrote before, and you now integrate over tau prime, because it only appears here in the, if you assume, if you write a spectral decomposition of the undeformed partition function as the expected sum over energy eigenvalues and momentum eigenvalues, delta and p, then you can plug this into here and then do the tau prime integration, which sets S1 equals 2 pi times the momentum, and it gives you, and you can also do the tau 2 prime integration, and that gives you a logarithmic branch point, and after some thought you realize that the contour runs in between these two branch cuts, and if you pull the contour back, you only get the contribution from S minus, and that gives you this homological spectrum for states with non-zero momentum. I see I have a note here to talk about what happens when alpha is negative, which corresponds to the holomorphic sign. But I don't have time now. If someone wants to ask me a question about that at the end, I'm happy to try to address this. Okay, so I'm moving on. So now we're going to talk about the mathematical version. So I talked about the partition function on a torus, but it's easy to talk in the same way about the one-point function on the torus, where we evaluate the expectation value of a local operator at the point x. And of course, this has to be independent of X by translational invariance. So it has to have the scaling form of R1 to the minus the scaling dimension of the operator phi times something which only depends on this dimensionless deformation parameter alpha, which is lambda divided by the area, and the modular parameter of the torus. So because this thing we expect to be modular invariant under the form modular group on the torus, it means that F alpha is going to be a modular form of weight out of phi. And in then going through the previous arguments, trying to prove that if f of 0, the unperturbed one, is modular, is a modular form of weight out of phi, then f of alpha is. You realize that you can play this game, in fact, with any modular or indeed Jacobi form. And it doesn't have to be anything connected with a conformal field theory at all. So this is basically the content of my recent paper. So I'll just quote a couple of theorems from that.
May I ask a quick question?
Yeah, sure.
Sorry, so I was just wanting to understand a little what the definition of this expectation value, this 1-point function is. So should I imagine that as it's an operator in the undeformed theory? I calculate its 1-point function and I plug that 1-point function into this integral kernel. Is that the way to understand what this?
More or less.
Because sort of the definition of operators in the deformed theory is a bit tricky.
Yes, it is. If I do it at the point X and I use the prescription that I gave before, that it corresponds to a diffeomorphism, or if you like, a displacement, because there's no displacement at the point X, essentially, it's the same operator. Okay. And I showed in a previous paper that you only get logarithmic divergences anyway, but the coefficient of the logarithmic divergences is given by the Ward identity as being proportional to the derivative of phi, which vanishes, whose expectation value vanishes by translational invariance. So this is in fact a finite quantity. Okay?
Perfect, thank you.
All right, so what the Earth's theorem is basically an abstraction of the proof that the proof of the first theorem is an abstraction of the proof that you need to prove this quantity is a modular form. So if we take any real modular form, because of course the expectation value of phi is real, so there's not a holomorphic modular form, it's a real modular form of weight k, so that under S it transforms according to the modulus of tau by the power k, and it's invariant under T, and so it has an expansion of the form here in powers of Q basically. Then the deformed form is this horrible expression here, which you get by doing that contour integral in S that I talked about. So here you see the deformed homological spectrum, but here these are the matrix elements. These are the deformed matrix elements of this operator X phi between the deformed eigenstates. Anyway, the mathematical theorem states that if this is a modular form, then this, which you can think of as the deformed modular form, also satisfies, is also a real modular form of weight K. Of course, it doesn't have a simple Q expansion anymore because of all these square roots here, but nevertheless, it has the same modular properties.
How do you know that this?
Yeah.
So how do you know that this deformation is the right one for an arbitrary one-point function? Because that will in general depend on. I mean, the one-point function in general depends on a lot of data, like the OPE coefficients.
Well, look, I think that is not really my point of view here. My prescription may or may not be the right prescription for the one-point function of a deformed conformal field theory. It is my definition, and the point is that if I use that definition and I apply the same arguments to this purely mathematical object, then I get this mathematical theorem. Okay.
Uh-huh.
And
okay.
if you stare at this object here, if somebody gave you this object here, you would be very surprised if it enjoyed these properties here with alpha here instead of 0. Okay. So another theorem in my paper is that if you now take a holomorphic form of weight K and you deform it more or less in the same way, that is, imagine that you've got this series here, but with P equals 0 basically, then if you take its Mellin transform, which is defined in this way, then under the TTbar deformation, the Mellin transforms in a very simple way. So if we take the undeformed Mellin transform and we multiply it by I, which happens to be the universal anti-function, which happens to be related to a confluent hypergeometric function, then, well, I should say that one nice property of the Mellin transform of a holomorphic form of weight K is that it's satisfies a reflection identity, rather similar to that satisfied by the theta function. So for alpha equals 0, this is a consequence of modular invariance, and it continues to be true. And for alpha equals 0, then the Mellin transform of a holomorphic form is related to a Richelet series, apart from some factors which I've not inverted here, of gamma of S and so forth. So if we have a Dirichlet series like this, which might be a zeta function, for example, and we form the corresponding holomorphic modular form, and then we deform that and we take the Mellin transform of that. That Mellin transform inherits the zeros of the original Dirichlet series. So if this were the Riemann theta function, it would inherit the Riemann zeros. for example. Of course, this does not lead to a proof of the Riemann hypothesis, but it gives you some interesting consequences. A third theorem is that if you talk about a mass form, I would love to know how to pronounce this word. If somebody has the correct pronunciation, maybe they can tell me afterwards. Then a mass form is essentially a smooth, non-holomorphic modular invariant, which happens also to be an eigenfunction of the invariant Laplacian on the hyperbolic plane. Then, in fact, what we find is that a deformed version of a mass form using the same prescription as before is just a constant depending upon alpha times the original mass form. So essentially all mass forms are eigenfunctions of the TTbar flow. So there's a very close connection between the TTbar deformation and mass forms. Any questions about that before I end the diversion? Okay.
So if I can write so you're saying if I can take any quantity like partition function and write it as a sum of mass forms.
Well, there's a problem. So the mass forms form a complete set of eigenfunctions with respect to the L2 norm on H. Unfortunately, if you take a partition function corresponding to a positive central charge, then it blows up in the corners. It blows up near the cusps, and so it's not L2 finite. So it certainly works for the partition function of a conformal theory with negative C, but otherwise you've got to think about ways of changing the definition of the partition function so it has the finite L2 norm. Which has certainly been tried in a paper by Benjamin et al. Okay, I'll move on because I see we're getting close to the end, so I just want to show you a nice picture at the end. Another way to go between ensembles is, of course, the Legendre transform, which is equivalent to the Laplace transform. It's equivalent to the steepest descent approximation to Laplace in the thermodynamic limit. And one way to get the thermodynamic limit is if we're in a holographic type conformal field theory, where the undeformed partition function goes exponentially with C at large C. But I do want to stress that the Legendre transform, anyway, is completely exact. The only point about the steepest descent approximation is it allows you to actually do it. But we can still think about doing it. So all these equations are, of course, completely conventional. The way you go between the fixed R1, R2 ensemble and the fixed N1, N2 ensemble is that you have the free energy and the force is the derivative with respect to the stress is the derivative with respect to the strain of the free energy. And then you solve these equations for R1 and R2 in terms of the stress, and then you And then you have the free energy in the fixed stress ensemble is related to by this Legendre transform here. And then if you want to get back the strain in terms of the stress, then you take the derivative of this with respect to n. That's a standard Legendre transform. Now, in our case, we know that in the fixed n ensemble that R of lambda evolves in this linear way. And so this has to be this. Therefore, this basically tells us how the free energy in the fixed stress ensemble evolves. It evolves in this very straightforward way. So this is explicitly modular invariant because what S and T do in the fixed stress ensemble is very simple. And this is explicitly invariant as long as this thing is. However, if we attempt to go back from this to the fixed strain ensemble, that's the fixed geometry, right? That is going from the undeformed fixed strain ensemble to the undeformed fixed stress to the deformed. This will fail. The Legendre transform will fail if the Jacobian happens to vanish. And as I'll briefly mention, this corresponds to the formation of a shock in the fluid analogy that I'll talk about on the next slide. Or it can happen if the area happens to go to zero, which corresponds to a collapse of the elastic sample. Because these R's have to be positive. So the fluid analogy is basically, if you think of these equations here as being the equations of a two-component, where A and B label the components of a two-dimensional fluid, in the Lagrangian or the particle picture, with lambda being time and the n essentially being the velocity. The equivalent Euler equations would then be these that is d by d lambda of the velocity is the velocity dot grad u, is u dot grad u, the standard way of writing the Euler equations. These are the generalizations of homologic of equation on the cylinder generalized to the torus. So the solutions to these equations may become singular, whilst the solutions to these equations do not, unless we form a shock or R goes to zero. And in fact, you can think of the equations of this fluid, which I have to stress is a non-interacting fluid. It's a very simple fluid. These can be thought of as if you take the Euler equations and you solve them by the method of characteristics, then you get essentially these linear equations here. So I won't go through this slide. You can see how all of this works in the case where the torus is very long and thin, and then you get the cylinder equations. But I guess I should say that you can see from this equation here that if lambda is zero, but the sample expands in the one direction and shrinks in the other. And what basically this shock is that you see that the particles all move at a constant speed, but the speed that they move at depends on where they started from. and the ones with a small r begin moving faster than the ones with a larger r, and they eventually overtake them, and that forms the shock. In fact, in your logo, you can basically see the formation of a shock here. If we've got R going up the board, lambda going across the board, then what is happening here is that the particles in the red that start from a smaller R are moving faster than the ones that start at a larger R, and they form this caustic or shock wave here. I'm not sure where this came from, but it's an interesting illustration of the formation of a shock or caustic. So if we do this in general, we've got Hayes equations here, and we can express the stress across the cylinder in terms of the stress tensor in this way here. So the nice thing about these equations here, this equals this, is that we can then, at any point in the moduli space, we can rotate to a basis where the stress tensor is diagonal and it's traceless, how it has formed. So in this fixed stress picture, we find that in one direction, the torus always expands, and in the orthogonal direction, it always untracks. And so if you work out how the area behaves, the area always decreases unless we're at a point in the moduli space where the stress tensor actually vanishes, where the eigenvalues of the stress tensor are 0. And there are such points in the moduli space by symmetry. So here's a picture of the moduli space in the standard way, where we talk about the tau plane and the principal region. And basically, this shows you how the TTbar, how the fluid flows, starting from a definite point in moduli space, and it flows along the lines of symmetry, but there are stagnation points where twice, because of the extra symmetry. For example, this point here corresponds to a tiling of the plane by squares. This point corresponds to a tiling of the plane by equilateral triangles. And at that point, the expectation value of the stress tensor on a torus like that will vanish identically, so there is no flow at all in this picture. So these are stagnation points of the flow. So what we basically find is that our equation here, that the area always decreases except at these stagnation points, means that something always happens. What actually happens is that for lambda negative, the area always goes to 0, and that corresponds to a collapse of the elastic sample. So that's the holomorphic sign of lambda. Whilst for lambda positive, what we get is that before the area goes to 0, we always get the formation of a shock wave. And so then we get a Hagedorn type singularity. But this whole picture here suggests that in the fixed stress ensemble, if these are the only singularities of going back to the fixed strain ensemble, that, in fact, modular invariance of the fixed grain partition function holds in a much larger region than we expect it to. And that will be interesting to understand. So I think I've gone on for longer than I ought to have done. Here's a summary. I'll just allow you to read it, and I would invite any questions if I haven't been clear so far.
Let's thank Professor Cardy. Questions?
Can you comment on the alpha negative or lambda negative case?
Yeah, I mean,
how you should make sense out of it?
Okay, so if you, well, certainly this general argument at the end, I stress, suggests that there's a range of alpha or a range of lambda for which you can define a modular invariant partition function. If you go back to the explicit expression in terms of that kernel, or if you go back to the explicit expression in terms of the contour, the inverse Laplace transform, it's possible to show that there is a choice of contour for which you get a modular invariant answer, but the answer cannot be then written as a sum over states in the standard way. So whether you want to call this a partition function when it's not a sum over states. Okay, there is an object which is modular invariant though.
Oh, I see. Okay.
So yeah, if I can tag on to that question. So
yeah, sure.
Is that the sense in which you sort of circumvent, I guess, the tension between, on one hand, saying for the wrong sign or whatever you want to call it. Yeah. I think in Chicago it's called the wrong sign. That you know, on one hand you would want to say, well, maybe I'll just keep a finite number of states to keep the partition function well defined, but you would just say that the thing that is modular invariant is just not written as a sum of states. So that's how I get away with maybe on one hand keeping a finite number of states for some well-defined fixed temperature partition function.
That when you look at that expression for partition function, as well as poles, it also has a branch cut. And the expression that you get for the modular invariant quantity involves a sum over a finite number of poles, which are the usual ones that you think about, and then an integral over a continuum. Now, what the physical interpretation of that continuum is, I don't know.
So yeah, you don't want to interpret that as some sort of continuous part of the spectrum.
Well, I mean, it looks like a continuous part of the spectrum, yes. But it's hard to understand why the spectrum would have a continuous part.
Okay, thank you. That was very helpful.
I had a very basic question. So your TTbarite, one weird thing, of course, is this infinite Poisson ratio, but also it doesn't have any nonlinear response, presumably.
Well, I'm just saying that the linear response will be that of something which has infinite Poisson's ratio.
But
So that corresponds to the fact that the partition function that I wrote down is really only well defined, that the quadratic form is not positive definite. So in order to define the partition function, you have to do some deformation of the consoles or something anyway.
Yeah, I was more concerned with higher order in
Higher
epsilon
order.
terms. Yeah.
Well, because you define TTbar as a flow, then you think about what you have as a particular value of lambda, and then you use that to define your elastic
Great.
response.
I see. Yeah. So it has a very definite kind of fine-tuned nonlinear elastic response, this TTbar.
Absolutely, yeah. Very, very fine-tuned. So that's why the TTbar deformation at finite lambda corresponds to a very, very fine-tuned addition of irrelevant operators or the theory of higher and higher dimensions.
Just out of curiosity, what's the biggest this Poisson ratio is in real world materials?
Oh, I think in two dimensions it's bounded between -1 and +1 or something. It's something like that. Whilst in 3 dimensions it's bounded between -0.5 and +1. And that comes from the positivity of the shear modulus, of the bulk modulus and the Young's modulus or something like that. Yeah.
If there are no more questions, let's thank Professor Cardy again.
Thank you very much.
Thank you. Thank you.
Bye
Let me
now.
pause the record. Bye-bye.